Module 2, Lecture A, Values and Types. By the end of this lecture, you will be able to identify and describe Python's basic data types, including int, float, string, and bool. Use built-in functions to check and convert data types in simple examples, and apply basic arithmetic and string operations to manipulate values. Python data types, working with numbers. In Python, numbers are one of the first data types you will use. Whole numbers are stored as integers, which are useful for counting things like students or products. Numbers with decimals use a different type, which is important for precise work such as financial or scientific calculations. Understanding the difference between these number types helps you predict how your data will behave in different situations. In Python, floating point numbers represent values with decimals, such as heights or prices, but they can introduce small rounding errors because of how computers store real numbers. This behavior is not unique to Python. It is common across most computer systems. As a result, numbers that look simple may not be stored with perfect precision. Being aware of this limitation is especially important in areas like finance or engineering, where even tiny differences can matter. In Python, it is important to choose the right numeric type and understand how operations behave with each one. Integers represent whole units, while floating point numbers represent quantities that can include fractions. Python often mixes these types in expressions and usually converts results to floating point for flexibility. By recognizing the difference between whole and fractional numbers, you can model quantities more accurately and ensure your programs handle numeric data correctly. Python code, working with numbers. This lesson uses simple, everyday numbers to show the difference between integers and floats. Integers are whole numbers, while floats include decimal fractions. By performing and printing basic arithmetic with both types, you can clearly compare how calculations with whole numbers differ from those with decimal numbers. This comment simply notes that while you could install an example library, standard Python is enough to run the script. In other words, the code does not depend on any extra packages. This makes it easy to use for anyone with a basic Python setup. No additional installation steps are required. We create a variable to store the number of apples in a basket and set its value to 7. This value is an integer because we are counting whole, separate items. Using an integer is appropriate for this kind of count and lets us easily perform arithmetic later, such as multiplying the number of apples by the weight of a single apple to find the total weight. We use a floating point number to represent the weight of a single apple in pounds, so we can include fractional values, not just whole numbers. This is important because real measurements often are not exact integers. Using a float helps keep calculations accurate, especially when we multiply this weight by other values, such as the number of apples. In short, the float data type preserves the precision needed for realistic weight measurements and related computations. To find the total weight of the apples, multiply the number of apples, which is an integer, by the weight of one apple, which is a decimal value. This calculation combines an integer and a float. The result is a float that represents the total weight in pounds, allowing for fractional values. We store the number of apples as an integer in a variable and then print that value. This shows that integers are used to represent whole numbers. Using an integer here makes it clear we are counting discrete items, such as individual apples. This line of code prints the weight of a single apple, which is stored as a floating point number, so it can include decimal values. Using a floating point type allows the weight to be represented with the precision needed for accurate calculations involving fractions. The print statement combines a short description with the actual weight value so the listener clearly understands what the number refers to. This line outputs the total weight of the apples in pounds as a floating point number, which allows for decimal values and more precise measurement. It shows the result of multiplying the whole number of apples by the decimal weight of each apple. By printing this value, we demonstrate how integer and floating point arithmetic work together to produce a fractional numeric result. We define a variable for miles driven and give it the value 12.5. This value is a float, meaning it can represent fractional numbers instead of only whole numbers. In this case, it represents the distance traveled in miles with greater precision. Such precision is important in distance calculations, where even fractions of a mile can matter. We define a variable that stores the amount of fuel used as a floating point number. In this example, it holds a value of 0.8 gallons. Using a floating point type is important because it can represent fractional amounts, which allows for more precise calculations in situations like measuring fuel consumption. To find miles per gallon, divide the total miles driven by the gallons of fuel used. This uses decimal or floating point division, so the result can include fractions of a mile per gallon. The outcome tells you how efficiently the vehicle uses fuel, expressed as how many miles you can travel on 1 gallon. This line outputs the miles per gallon value as a floating point number. It is calculated by dividing the miles driven by the gallons of fuel used. The result shows fuel efficiency with decimal precision. This script shows how basic arithmetic works with whole numbers and decimal numbers using simple, everyday examples. It first multiplies an integer number of apples by a decimal value for the weight of one apple to find the total weight, demonstrating how integers and floats interact. It then divides miles driven by gallons of fuel, both as decimal values, to calculate miles per gallon and illustrate float division. Overall, it highlights the difference between whole number and decimal arithmetic and how both are used in practical situations. Working with strings. In Python, written information is stored as strings, which are sequences of characters such as letters, digits, and symbols. Whenever you work with text in a program, like a book title or an email subject, you are using a string. Even if a string contains numbers, such as a phone number, Python still treats it as text, and this affects how you can process and manipulate it in your code. In Python, strings are dynamic sequences of characters that you can explore and work with in flexible ways. Each character has a position, so you can access single characters or segments, which is useful for tasks like pulling out parts of an email address or a product code. You can also check how many characters a string contains, which helps when validating inputs such as passwords. Thinking of strings as sequences provides a clear conceptual foundation before you focus on the exact syntax for these operations. In Python, strings let you combine and modify text in flexible ways. You can join separate pieces of text to build messages, such as greetings or addresses, and you can repeat strings when needed for formatting. Python also provides tools to change the case of letters, remove extra spaces, and replace parts of the text. These capabilities make strings a powerful way to handle text in many kinds of applications. Python code, working with strings. In this lesson, you will work with basic strings in Python by creating them and examining their contents. You will see that a string is an ordered sequence of characters, each with its own position in the sequence. You will also practice combining strings, taking slices of them, and applying simple transformations. Together, these activities illustrate the most common ways to inspect and manipulate strings in Python. This line is a placeholder comment indicating where you would add a command to install a required library for the script. It serves as a reminder to make sure all necessary dependencies are installed before running the code. This is especially important when sharing the script with others who may not have the same environment set up. We begin by creating two simple text values to represent a person's name. One value stores the first name, Alice, and another stores the last name, Johnson. These basic pieces of text will be used later to show how Python can combine and work with string data. In this example, we create a full name by joining the first name and last name into one string. We do this by placing a space character between them and combining all three parts. The result is a single piece of text that represents the person's full name. This makes it easier to store, display, and work with the name as one complete value. This line combines the first and last names to form a full name, prints that full name, and also shows how many characters it contains. It uses a length function to count the characters in the full name string. The count includes every character, including spaces between the names. In this example, we access the first and last characters of a full name string using Python's indexing. An index of 0 gives the first character at the start of the string. A negative index of 1 gives the last character, since negative positions count backward from the end. This shows how indexing lets you quickly reach specific positions within a string. In this example, we take a slice of the full name string to extract only the first 5 characters. We do this by specifying a range that starts at the beginning of the string and stops just before the 5th position. The resulting substring is then printed, showing the initial segment of the full name. This approach is useful when you want to quickly preview or validate part of a text input. In this example, we create a value that looks like a number, such as a zip code, but we store it as text rather than as a numeric type. This distinction matters because treating it as a string preserves any leading zeros that might otherwise be lost if it were converted to a number. Keeping the zip code as text also allows you to perform operations that are specific to strings. Overall, storing it as a string ensures it can be displayed and manipulated exactly as written, without unintended numeric conversion. Here we show that a zip code even though it looks like a number, is actually stored as text. We display the zip code and then check its data type using a type checking function. This confirms that the zip code is treated as a string rather than a numeric value. Recognizing it as text is important because it should be used in text processing operations, not in numerical calculations. This line takes a full name and creates two versions of it, one in all uppercase letters and one in all lowercase letters. It uses a method that converts every character to uppercase and another that converts every character to lowercase. This shows a basic way to change the letter case of a string, which is useful for making text input or output consistent. Both versions are then printed together so you can easily compare the uppercase and lowercase forms. To create a simple visual separator in console output, we build a string made of 20 dash characters by repeating the dash 20 times. Printing this string produces a clear horizontal line. This line acts as a visual break in the output, helping organize or highlight different sections of printed information. This script demonstrates basic string handling in Python by creating separate first and last name strings and combining them into a full name. It then prints the full name, its length, and shows how to access the first and last characters, as well as a slice of the first few characters. The script also includes a zip code written as text to highlight that it is still treated as a string, not a number. Finally, it converts the full name to uppercase and lowercase and creates a simple separator line by repeating a dash character, illustrating common ways to manipulate, inspect, and format strings. Boolean values and logic. Boolean values in Python are a basic data type that represent only two states, true and false. They are different from numbers and strings, but often interact with them, serving as answers to yes or no questions, such as whether a user is logged in or a payment has gone through. Programs use Booleans to make decisions, like granting access only if terms and conditions are accepted. Because of this, understanding Booleans is essential, as they form the foundation of decision-making and control flow in programming, even in simple scripts. Boolean logic extends simple true and false values by combining them with operations called and, or, and not to evaluate more complex conditions. For instance, a streaming service might require that a user is both a subscriber and in a supported region, while an online store might give discounts to students or loyalty members. The not operation reverses a true or false value, such as checking that something is not expired. Together, these operations let programs express detailed rules for tasks like security checks and filtering search results. In many programming languages, different data types can behave like true or false, depending on their content. Empty values, such as an empty string, the number 0, or an empty list, are usually treated as false, while non-empty or non-zero values are treated as true. This allows quick checks, such as whether a form has text, an account balance is not 0, or search results contain items. However, it is important to distinguish between actual Boolean values and other types that only act like Booleans, so you avoid logical errors and better understand how your program behaves. Python code, Boolean values and logic. This section introduces basic Boolean values and logical operators in Python. It explains how conditions can be combined using the words and, or, and not to form more complex tests. It also shows that non-empty values are treated as true when used in Boolean checks. No extra libraries or installations are required for these concepts. We define 3 Boolean variables to describe a user's status. One indicates the user is currently logged in. Another shows the user has not accepted the terms and conditions. And a third marks the user as a premium member. These true or false values will later be used together to decide what level of access and benefits the user should receive. To decide if a user can access the full site, we check 2 conditions. The user must be logged in, represented by a true or false value, and must have accepted the terms. Both of these conditions must be true at the same time. This is enforced using the logical AND operator, which only grants full access when both requirements are satisfied. In this example, we decide whether a user gets a discount by checking 2 conditions. The user qualifies if they are a premium member, or if they have accepted the terms. Because we use a logical OR, meeting just one of these conditions is enough. This makes the rule more flexible, since either requirement can grant the discount. We want to check whether the user needs a reminder to accept the terms. And we do this by flipping the value of the condition that tracks if the terms have been accepted. When that original condition is false, using the logical NOT operator turns it into true, which means the user still needs a reminder. This shows how the NOT operator quickly inverts a condition, so we can easily detect the opposite situation. We store the text value Alice in a variable that represents a username. In Python, any string that is not empty counts as true when used in a condition. This means we can later check whether a username has been set simply by testing the variable in a conditional statement, without needing an extra comparison. In this example, we are checking the Boolean value of a non-empty username string. In Python, any string that is not empty is considered truthy, which means it evaluates to true in a Boolean context. Using the Boolean conversion makes this explicit by turning the username into its true or false form. This provides a simple way to test whether a username was entered without directly comparing it to an empty string. This line displays a message in the console that tells you whether the user can access the full site. It relies on a Boolean value that was already calculated from the conditions of being logged in and having accepted the terms. By printing this result, it makes the outcome of the logical check clear for anyone reviewing or testing the code. This line outputs whether the user receives a discount benefit. It relies on a value that was set earlier by checking if the user is a premium member or has accepted the terms. The message clearly shows the result of this logical check so the user can see if they qualify for the discount. This line displays whether the user still needs a reminder to accept the terms. It relies on a previously defined true or false value that indicates if the terms have not been accepted. Based on this value, the output clearly shows if a reminder is required at the current moment. This example shows how Python decides whether a non-empty string is considered true. A variable stores the result of converting the username string into a Boolean value. Because the username string is not empty, this conversion produces the value true. The program then prints this result to demonstrate that any non-empty string is treated as truthy in Python. This script shows how Boolean logic works in Python by deciding user access and benefits based on their status. It first checks if the user can access the full site, which requires both being logged in and having accepted the terms. So access is denied when the terms are not accepted. It then checks if the user gets a discount by seeing if they are a premium member or have accepted the terms. And in this case, the premium status is enough to grant the discount. The script also decides that the user needs a reminder to accept the terms, since they have not done so yet. Finally, it evaluates a non-empty username as true in a Boolean context and prints all these results about access, discounts, reminders, and username truthiness. Inspecting data types. Checking types with type ... In Python, it is not always obvious what type of data you are working with just by looking at a value, especially in larger programs. To help with this, Python provides a built-in function that tells you the data type, such as integer, float, string, or Boolean. This is like asking Python what label it has given to a particular piece of data. For example, if you receive a user's age from a form, you can check whether Python treats it as a number or as text. Confirming the type helps you understand how you can use that value and avoid unexpected problems in your code. When working with data from files or user input, it is important to use Python's type checking to see whether values are treated as text or as numbers. Even if something looks like a number, it may actually be stored as text, especially in tools like budgeting or survey applications. By checking the type, you can decide whether you need to convert the value or handle it differently. This helps keep your code more robust and reduces errors by confirming your assumptions about the data. Regularly checking data types in Python is important for understanding errors and planning what operations are possible. When a calculation, such as an average satisfaction score, fails, checking the types can reveal problems like mixing numbers with text or using a Boolean where an integer is expected. Noticing these differences helps you decide what conversions are needed and which operations are valid. Over time, you will learn to anticipate the expected types in your programs and use type checking as a quick way to diagnose issues. This habit leads to more reliable programs that can handle real-world data effectively. Python code. Checking types with type. In Python, you can check what kind of value you are working with by using the built-in type function. When you print the result of this function for different values, you will see that numbers, text, and other data each have their own type. This helps beginners understand how Python is interpreting the data they use. It is especially useful when inspecting values that come from user input or from files, because it makes the data format clearer and easier to work with correctly. This line explains that you do not need to run any installation commands because the script uses only features that come built into Python. All the functionality it demonstrates is available in a standard Python setup. As a result, you can run the script without adding external libraries, which keeps things simple and accessible for anyone using Python. This example introduces 4 basic data types in Python by assigning values that represent a person. An integer is used for age in years. A floating point number is used for height in inches. A string holds the person's name, and a Boolean value indicates that the person likes Python. Together, these values show how Python can store whole numbers, decimal numbers, text, and true or false information. We use Python's type checking function to print each variable's value along with its data type. This shows that the age value is stored as an integer, and the height value is stored as a floating point number. It also confirms that the name value is a string, and the preference for Python is a Boolean. Together, these checks demonstrate how to inspect and verify the types of different values in a Python program. In this example, we simulate reading a value from an external source by storing the text 42 in a variable and then printing both the value and its type. We use the type checking function to confirm that even though it looks like a number, the value is actually stored as text. This highlights that data read from files or other sources is often interpreted as text, even when it appears numeric, and shows why checking the data type is important. We use a conversion function to turn a number stored as text into an actual integer so it can be processed numerically. This is important when data is read in as strings but needs to be used in calculations. After converting, we display the value and its data type to verify that the conversion worked. This confirms the data is now in a proper form for numerical operations. This script shows how to inspect and change data types in Python using the built-in type function. It defines several values, such as an integer, a decimal number, a piece of text, and a true or false value, and prints each one, along with its type, to show how Python classifies them. The script then pretends to read a number stored as text, displays that it is treated as a string, converts it to an integer, and prints the new type. Overall, it provides a simple example of checking and converting data types to better understand how Python handles different kinds of values. Decoding error messages. When you try different values and data types in Python, error messages are useful feedback, not something to fear. Many beginner mistakes come from combining incompatible types, such as mixing numbers and text. When this happens, Python stops and shows an error that explains what went wrong and which types were involved. By reading these messages carefully, you can treat them as clues that help you inspect and correct your data types. This mindset turns errors into a tool for learning how Python handles data. When Python shows an error message, it usually tells you which operation failed and what types of values were involved. For example, adding a number to text in a budgeting script or mixing text and numbers in data analysis can cause type or sorting errors. These messages are a signal to check the types of your values, for instance, by printing them or using a function that shows their type, and then converting them if needed. With practice, you will start to anticipate these type mismatches, especially when working with user input or external data. When you read error messages, focus on where in your code the problem occurs and which value is causing it. For instance, If a grade is left as text instead of being converted to a number, the error will appear when you try to calculate the average. Use the error message to trace back to the point where the conversion was missed. This habit helps you pay attention to data types and make sure each operation uses compatible values, which leads to fewer type mismatches and more reliable code. Python code. Decoding error messages. Type mismatch errors happen when you try to use values of incompatible types together. And it is important to learn how to read these error messages. They usually mention the operation that failed and the data types that were involved. By paying attention to this information, you can quickly see which values do not match. Often, you can fix simple mismatches by checking the types you are using and converting them to compatible types when needed. The commented out installation command shows that this library is not needed for the current script. It likely comes from an earlier version or a different context where that dependency was required. This highlights that setup code can sometimes be unnecessary, so it is important to review it and comment out or remove lines that are not actually used. Doing so keeps the script cleaner and easier to understand. We define a helper function called try operation that takes a description and another function representing an operation. Its purpose is to run that operation safely. Inside, it uses a try block to attempt the operation and, if it works, prints a success message with the description, the result, and the results type. If an error happens, an except block catches it and prints the description along with the full error message, helping us understand what went wrong. We assign the number 10 to one variable and the text 5 to another to show the difference between numeric and textual data. The number represents a value we can use in calculations, while the text is only a written form of that number. If we try to add these two values together without first converting the text into a numeric type, Python will treat this as mixing incompatible types. This usually leads to a type mismatch error, highlighting the need to convert text to a number before doing arithmetic. We use a helper function to show a type mismatch error by testing an operation described as adding a number and text directly. It runs a small function that tries to add a number to a string, which Python does not allow. This causes a type error because numbers and strings cannot be added together. The helper function catches this error and prints a message indicating that the operation failed, along with the error details. To fix the type mismatch, we first convert the text value to an integer before adding. We then add the numeric value 10 to the converted value 5, so both operands are integers. This prevents errors caused by mixing text and numbers. The final result of this addition is stored in a variable called fixed sum. This line prints a message showing that the addition now works correctly after converting the text value to an integer. It outputs the result of the addition, stored in the fixed sum variable, and also reports its data type. By confirming that the result is an integer, it shows that the type mismatch problem has been successfully resolved. In this example, one value is stored as a number, such as 85, and another is stored as text that looks like a number, such as the word 90. This setup is used to show what can go wrong when you compare a true numeric value with a value that only appears numeric but is actually text. The key idea is that operations and comparisons depend on compatible data types. So, mixing numbers and numeric-looking text can lead to errors or unexpected behavior. In this example, a helper function is used to show a type mismatch error by calling it with a description of the operation and a small function that compares a number directly with a text value. Even if the text looks like a number, Python treats it as a string, so comparing it directly with a numeric value causes a type error. This demonstrates how Python reports such errors and highlights the need to make sure the values you operate on are of compatible types. To correctly compare a numeric value with text that looks like a number, you should first convert the text into an integer. This makes both values the same type and allows a valid comparison. The code then checks whether the numeric score is greater than the converted score and produces a true or false result. Converting the text first prevents type mismatch errors and keeps the comparison logically correct. The code demonstrates a corrected comparison by first converting a text value into an integer. It prints a message explaining that the comparison has been fixed using integer conversion, then shows the outcome of the comparison. This outcome is a Boolean value, so it is either true or false. Finally, the code confirms that the type of this result is indeed Boolean. This script shows how mixing incompatible data types in Python can cause errors and how to fix them. It first tries to add a number and a string, which raises a type error that points out the mismatched types. Converting the string to an integer makes the addition work and lets you see the correct result and its type. The script then repeats this idea with a comparison between a number and a numeric-looking string, which also fails until the string is converted to an integer. Overall, it highlights how reading error messages and using type conversion can resolve simple type mismatches and help with debugging. Automatic type conversion. Python automatically converts data types behind the scenes to keep operations running smoothly, especially when combining compatible types like whole numbers and decimals. For example, if you add a whole number to a decimal number, Python converts the whole number to a decimal, so the result is precise. This automatic conversion reduces the need for manual type handling and makes common tasks such as working with measurements or prices more straightforward for the programmer. Automatic type conversion in Python follows rules that convert more specific numeric types into more general ones to avoid losing information. When you combine a whole number with a decimal, Python automatically turns the whole number into a decimal. This keeps the result precise, such as when calculating totals that mix whole and decimal prices. In short, Python promotes values to a more expressive numeric type, so calculations preserve detail. Automatic type conversion in Python has limits, and understanding them helps you avoid surprises. Python will not automatically convert between very different types, such as text and numbers, because that could cause errors. This means that when you work with mixed data, like survey responses that include both words and numbers, you must explicitly decide how to convert them. Although Python can handle many mixed numeric operations on its own, You should be prepared to use conversion functions when reading data from files or user input. Knowing when Python will and will not convert types gives you better control and makes your programs behave more predictably. Python code, automatic type conversion. When you mix different numeric types in arithmetic, most languages automatically convert integers to decimal floating point values, so the calculation can be done in a consistent way. This means that if an integer is combined with a decimal number, the result is treated as a float. However, this automatic conversion does not extend to strings and numbers. Strings and numeric values are not automatically converted to each other, so they cannot be directly combined in arithmetic without an explicit conversion step. This line is a placeholder comment reminding you to install any required libraries before running the code. It marks where you would add a command that uses Python's package installer, pip, to install a needed dependency. The main idea is to ensure all necessary libraries are installed so the script can execute correctly. We define a variable to store a distance in miles and give it the whole number value 5. Using an integer type here means the distance is represented as a whole number. This choice also allows us to perform arithmetic with the distance later, and Python will handle any needed type conversions automatically. We use a floating point number to represent a distance in miles so we can include decimal values for more precise measurements. Setting the distance to 2.5 means it is automatically treated as a float in Python. This allows any arithmetic with that value to work smoothly with other numeric types and maintain the needed precision. When you add an integer and a float in Python, such as 5 miles and 2.5, Python automatically converts the integer to a float to perform the calculation. This automatic conversion ensures the result is a float, which preserves decimal precision. As a result, the combined distance is stored and handled as a floating point number. This line outputs the total distance obtained by adding an integer value to a floating point value. During this operation, the integer is automatically converted to a float, so the calculation is done in floating point form. It then prints the data type of the result, confirming that the combined distance is stored as a float. In this example, we calculate average speed by dividing 60 by 4.0, which mixes an integer with a floating point number. In Python, this kind of division automatically produces a floating point result. This behavior preserves precision and reflects the type of the divisor. It is the usual outcome when performing arithmetic with mixed numeric types in Python. The code prints the value of the average speed and then shows its data type. The average speed was calculated by dividing 60 by 4.0, which produces a floating point number. After displaying this value, the code prints its type, confirming that it is a float. This illustrates that in Python, dividing an integer by a float results in a float. In this example, a variable is set to the text version of the number 3, meaning it is stored as a string rather than as a numeric value. This situation often occurs when data comes from user input or files, where numbers are initially read in as text. Understanding this distinction is important because text values must usually be converted before they can be used in numeric calculations. When you have a number stored as a string and want to do arithmetic with an integer, you must first convert the string to an integer. In this example, the miles value written as text is turned into an actual number using the integer conversion function. After this conversion, it can be safely added to another integer distance. This step is required because Python does not automatically change strings into numbers during calculations, and trying to add them directly would cause an error. This example shows how a numeric string is converted to an integer before doing arithmetic. The code turns the string into an integer, adds it to another integer, and then prints the total miles. It also checks and confirms that the result is still an integer. Overall, it demonstrates explicit type conversion from a string to an integer to ensure correct numeric calculations. This script shows how Python automatically converts data types during arithmetic. When you add an integer and a float, or divide an integer by a float, Python converts the result to a float, which you can see in the combined distance and average speed calculations. However, Python does not automatically mix strings and numbers, so a numeric value stored as text must be explicitly converted to an integer before you can add it to another number. After this conversion, the script confirms the result as an integer total. Working with operators, basic arithmetic operators. When you start using Python, you will often combine and transform numbers using basic arithmetic operations, much like everyday calculations. These operations include addition, subtraction, multiplication, and division, and Python evaluates them to produce a result. Understanding how these operators work is important, because even small mistakes in how you combine numbers can lead to incorrect outcomes in your programs. This matters for simple tasks as well as for more advanced work like data analysis or simulations. In addition to basic arithmetic, Python includes operators for remainders and exponentiation that let you express more complex numerical ideas. The remainder operator tells you what is left after division, which helps when checking if quantities divide evenly or when cycling through repeated options. Exponentiation raises a number to a power and is widely used in areas like science and finance for modeling growth or calculating interest. By combining these operators thoughtfully, you can represent real-world numerical relationships in a clear and concise way. When doing arithmetic in Python, it is important to know how expressions are evaluated and how different numeric types work together. Python follows the usual order of operations, so multiplication and division are done before addition and subtraction unless you use grouping to change that order. Grouping parts of an expression can change the result and makes your intent clearer. When you mix whole numbers and floating point numbers, Python usually produces a floating point result, which is useful for more precise calculations. Keeping these rules in mind helps you predict outcomes and avoid errors in your programs. Python code, basic arithmetic operators. This lesson shows how basic arithmetic operators work using simple, everyday-style examples. It demonstrates addition, subtraction, multiplication, division, the remainder after division, and exponentiation. For each operator, the result is printed clearly so beginners can easily hear and understand how the numbers change. The goal is to make the effect of each operator obvious and easy to compare. This comment explains that no installation commands are needed because the example does not use any external libraries. Instead, it relies only on Python's built-in features to perform basic arithmetic. This design choice keeps the code simple and focused. It also makes the example more accessible for learners who are just starting to explore arithmetic operations in Python. We begin by creating an integer variable called number1 and giving it the value 15. This establishes a starting value that we can use in later arithmetic. With this base number in place, the script can perform operations such as addition and subtraction when it is combined with another number. We now create a second integer variable and give it the value 4. This new value will be combined with the first integer in later examples. Using this second number lets us demonstrate how different arithmetic operators behave when they work with more than one integer value. In this example, we add two integer values and store the result. A variable is assigned the value obtained by adding the first number and the second number. This operation simply combines the two numbers into a single sum. The resulting value can then be used or displayed later as needed. Subtraction finds the difference between two numbers by taking the second number away from the first. In this operation, the value of the second number reduces the value of the first, and the result is called the difference. This simple arithmetic process is used in Python to demonstrate how subtraction works in code. Multiplication lets us scale one value by another. In this example, we take 15 and multiply it by 4 to get their product. That result is then stored in a variable called product result. This shows how multiplication combines quantities in a simple, direct way. Division tells us how many times one number fits into another. In this example, we divide 15 by 4 to find the quotient. This quotient shows how many equal parts of size 4 can be taken from 15, or how the first number can be distributed into groups defined by the second number. The remainder operator gives the amount left over after dividing one number by another. For example, when you divide 15 by 4, the remainder operator returns what is left after taking out all the full groups of 4. This idea is useful for checking properties of numbers, such as whether a number is even or odd. It is also helpful in cyclic situations, where values repeat after reaching a certain limit and then wrap around. In this example, we use exponentiation to raise the number 2 to the power of 3, which means multiplying 2 by itself 3 times to get 8. We then store this result in a variable called exponent result. This stored value can be used later in the program to display or work with the outcome of the calculation. The code prints the results of 3 basic arithmetic operations, each with a clear label. It first shows the sum of the two numbers, then the result of subtracting the second number from the first, and finally, the product of the two numbers. The labels make it easy to tell which operation produced each result. This code prints the results of 3 arithmetic operations on two numbers. It first shows the quotient when the first number is divided by the second. Then, it prints the remainder from that same division. Finally, it displays the second number raised to the third power. Each printed value is labeled so you can easily tell which operation produced it. This script uses the integers 15 and 4 to to demonstrate basic arithmetic operations. It calculates and prints their sum, difference, product, and quotient, as well as the remainder when 15 is divided by 4. It also shows the result of raising 4 to the power of 3. Each output is labeled to clearly illustrate these fundamental operations. Joining strings together. In Python, joining pieces of text into one message is called concatenation. It lets you build larger strings from smaller parts, such as combining a first and last name or merging a product name with its price. The key idea is to arrange these text fragments in a clear order, so the final result reads naturally like a sentence. This skill is important for creating user-friendly output, writing log messages, and generating dynamic content for applications or websites. When you join text in Python, every part you combine must be a string. If you want to include numbers or logical results, such as an age or a calculation, you need to convert them to strings first. Doing this prevents errors and lets you place these values anywhere in your message. It also gives you flexibility to shape your output for different users and situations. When working with strings, you need to include spaces, punctuation, and formatting so the text is clear and readable. If you join words without spaces or separators, they run together and look unprofessional, especially in user-facing messages. Be deliberate about adding spaces, commas, and other separators when combining parts like a greeting, a name, a date, and a time. This attention to detail keeps your output both technically correct and polished for real-world use. Python code, joining strings together. This section focuses on how to join separate pieces of text into clear, readable messages. It explains that non-text values, such as numbers, must be converted to text before they can be combined with other words. It also emphasizes paying attention to spaces and punctuation so the final output looks and sounds like a proper sentence. Together, these ideas help you build clean, understandable text output from multiple parts. This line explains that you do not need to run any installation commands because the script uses only features that come built into Python. All the functionality it relies on is already available in a standard Python setup. As a result, the code is simpler to use and easier to move between different systems without extra setup. We define two separate string variables to store a first name and a last name, such as Alex and Johnson. These separate pieces let us work with each part of the name independently. Later, we combine them with a space in between to form the full name. This method makes it easy to manipulate or change individual name components before creating the complete name. To form a full name, you combine the first name and the last name with a single space between them. This creates one complete string that clearly represents the person's name. Using this combined full name makes it easier to read, display, and use in messages or other outputs. We create a variable to store a person's age in years and set it to 28. This lets us keep the age information ready for later use, such as building messages or doing calculations. By saving the age as a number, we can easily perform any arithmetic operations we might need. When we store a person's age in a program, it is usually kept as a number. but to use it inside a text message, we must convert it to a string. This means we change the numeric value into text so it can be combined smoothly with other words. A string conversion function performs this change, turning the number into a text format. Once converted, the age can be joined with the rest of the message without any issues. We build a friendly message by joining together the word hello, the person's full name, and their age. We include a comma and a space after the name to keep it readable. Then add the phrase, "You are to introduce the age." The age value, which has already been converted to text, is then attached. Finally, we add the words "years old" to complete a clear, natural-sounding sentence. We define one variable to store the product name, set to wireless mouse, which identifies the item we are working with. We then define another variable to store the product price, set to 19.99 as a floating point number representing the cost in dollars. Together, these values will later be combined to create a clear message or receipt line that shows both the product name and its price. We convert the numeric price of a product into a string so it can be safely combined with other text when creating a readable message. This step is important because numbers and text are handled differently in many programming environments. By turning the number into a string first, we can join it smoothly with other words or phrases. This helps keep the final output clear and prevents errors during the concatenation process. We are building a readable text description of a product by carefully combining its parts with punctuation and spacing. The line begins with the word item, followed by a colon, a space, and the product name. After that, we add a comma and a space, then the word price and another colon. We then include a $sign to show the currency and finish by attaching the price value, converted into text, completing a clear, well-formatted product detail line. This code prints two messages to the console, a greeting and a receipt line. The greeting combines a person's first and last names with a space, converts the age from a number to text, and joins everything into one sentence. The receipt line does the same for a product, converting the price to text and formatting the name, price, and punctuation into a clear line. Both outputs demonstrate how to join text and converted numbers into readable messages for the user. This script shows how to join text and convert other data types into strings for clear output. It first combines a first and last name with a space to form a full name. Then it turns a numeric age into text to build a personalized greeting. It does the same with product information by converting a numeric price into a string so the message is readable and properly formatted. When run, it prints a greeting with the person's name and age, and a receipt-style line with the product and its price, emphasizing the need for correct type conversion, spacing, and punctuation. Boolean comparisons. In programming, Boolean comparisons are used to check relationships between values and produce results that are either true or false. For example, a program might test whether a user is at least 18 years old, whether a bank balance is negative, or whether two text entries are exactly the same. These true or false outcomes then guide decisions in the program, such as granting access or showing a warning. In this way, Boolean comparisons control how the program responds to different conditions. Boolean comparisons let programs decide how different kinds of data relate to each other. With numbers, you can check if one value is greater than, less than, or equal to another, which is useful in tasks like grading or tracking inventory. With strings, you often compare text to see if two entries match, such as in password checks or search features. Small differences in spaces or capitalization can change the result. So understanding these details is important for creating reliable comparisons that behave as users expect. Boolean comparisons become especially powerful when you combine them to handle complex conditions, much like real-world decisions. In programming, you link multiple true or false checks to express detailed rules, such as when to apply a discount, allow or block a login, or approve a reservation. Each comparison returns true or false, and together they guide the program to continue, ask for more information, or stop with a message. This lets your code model precise constraints and decision logic in a clear, structured way. Python code. Boolean comparisons. This lesson shows how to use simple Boolean comparisons with numbers and text, and how these comparisons always give a yes or no answer, represented as true or false. You will see how to check conditions, such as whether values are equal or different, and understand that each check produces a clear Boolean result. Finally, you will learn how to combine several comparisons to make a decision, such as whether a user is allowed to access something based on multiple rules. This commented line is a placeholder for installing any libraries the script might need. It is often placed at the top of a script to make sure all required dependencies are available before the rest of the code runs. Because it is commented out, it is optional and should only be activated if those libraries are not already installed. We create a variable to store the user's age and set its value to 19. This value represents how old the user is. Later in the program, we use this stored age to check whether the user meets the minimum age requirement for being considered an adult. Defining the age in one place makes it easy to reuse in comparisons and other logic throughout the code. We create a variable to store an account balance in dollars and set it to -5.25. This negative value represents an overdrawn account, meaning the balance is below zero. By initializing the balance this way, we can later use it to check the account's financial status in comparisons. We create a variable to store the first password entry as a text value. In this example, the password is secret123, which mixes uppercase and lowercase letters with numbers. This stored password is typically used later to compare with a second password input. The comparison must match exactly, including letter case, which is important for secure authentication. We create a second password entry as a string that is slightly different from the first one, to show that string comparisons are sensitive to capitalization and character case. This difference lets us test whether the two password entries match exactly. Such exact matching is essential for validating user input in systems like logins, where even a small change in case means the password is incorrect. We determine whether a user is an adult by checking if their age in years is at least 18. If the age is 18 or older, the check returns true, meaning the user is considered an adult. If the age is less than 18, the result is false, meaning the user is not an adult. This true or false value is stored for later use when deciding what access permissions the user should have. This step checks whether the account balance is below zero, which would mean the account is overdrawn. It compares the balance to zero, and if the balance is negative, it marks the account as overdrawn. This indicates the user has spent more money than they have available, and is important for deciding how the account can be accessed later. In this step, the program checks whether the two password entries match exactly, including capitalization. It uses an equality comparison to see if both text strings are identical. This is important to confirm that the user typed the intended password correctly, with no differences in letters or symbols. The result of this check helps decide whether access should be granted. To decide if a user can access their account, we combine several true or false checks. We confirm the user is an adult by making sure their age is at least 18, and we verify the account is not overdrawn by checking that the balance is not negative. We also require that the two entered passwords match exactly, including capitalization. All of these conditions must be true at the same time for access to be granted, which improves security and reliability. The code prints whether the user is an adult by showing a clear message with the result of the check. It reports the adult status as a true or false value based on whether the user's age is at least 18. It also includes the user's actual age to show how that result was determined. This makes the output both informative and easy to interpret. This line prints whether the account balance is negative, indicating an overdraft. It relies on a stored result that shows if the balance is below zero. The printed message also includes the current balance amount, so it is clear why the account is considered overdrawn. This line checks whether two password entries match exactly, including capitalization, and then prints the result. It reports if the passwords are identical or not. This confirmation helps ensure the user has entered the correct password with the proper case, which is important for security. The code prints a final decision about whether account access is allowed based on a combined true or false result. This result comes from checking three conditions. The user must be an adult, the account must not be overdrawn, and the passwords must match. If all these checks pass, the message indicates that access is granted. Otherwise, it indicates that access is denied. This script uses Boolean comparisons to decide whether a user can access an account based on age, account balance, and password matching. It checks if the user is at least 18 to confirm adult status, then determines if the account is overdrawn by seeing whether the balance is negative. It also compares two password entries exactly, including letter case, to see if they match. Finally, it combines these results to make an access decision and reports that the user is an adult, the account is overdrawn, the passwords do not match, and access is therefore denied. In this lecture, you learned to identify and describe Python's basic data types, including int, float, string, and bool. Use built-in functions to check and convert data types in simple examples. And apply basic arithmetic and string operations to manipulate values. In the next lecture, Lecture B, we will go over variables and input.
Thank you for your attention. See you all in the next lecture.